Hey, hi, welcome to the part 4 of the video of wind energy and wind turbine. So, up till now, what we have learned is how to up till now, what we have learned is the angle of attack. What's the significance of angle of attack? So, in this video, what we will do is we will learn how to give twist to the wind turbine blade. So it's very interesting to analyze why do we give twist to a wind turbine blade. Now you would have seen wind turbine blade. It looks something like this. Now if you carefully observe this blade, you will observe there is a twist in this blade from the root till the tip. Now the reason why we give the tip is very simple. It's very simple. Just imagine this is our wind turbine blade and it is rotating with some angular velocity, right? So this is our wind turbine plane. Right, so let's start from here. Right. Right. So just imagine. Right. So just imagine this wind turbine is rotating with some angular velocity omega. This is our omega. Right. Now what's going to happen? You know, your tip speed ratio is nothing but r into omega upon velocity of wind, right? So let's cut it. Let's cut this and paste it there. Control C. Right. So the tip speed ratio is nothing but radius times omega divided by velocity of wind. Now, say for example, somehow you have managed to make the tip speed ratio equals to 8 of the tip. When I say tip, it means this element. Up till now, all the videos we were discussing about elements. But actually, this wind turbine is made up of n number of elements. You can divide it into n number of elements, isn't it? So, what we want is, say for example, we divide this blade into 20 elements. So, imagine we have 20 partitions of this blade. Now imagine what each element is going through. Now when we say that the tip speed ratio is 8, right? When we say the tip speed ratio is 8, that means this element, the final element, this last element is experiencing a tip speed ratio equals to 8, right? But what about the other elements? There are 20 elements. This is element 1, this is second, this is third, this is fourth, this is fifth, sixth, seventh, eighth, and so on. And let this be the 20th element. Now, just imagine if this element is experiencing a tip speed ratio of 8. What would be the tip speed ratio of this element, which is the final element? Now, naturally, just think, tip speed ratio is nothing but radius times omega times the velocity of wind. Consider the first element and consider the last element. Now if you see, the only difference is the radius, the distance from the axis of rotation, both these elements are traveling with same angular velocity omega, and both these elements are experiencing the same wind velocity. Relative velocity will change anyhow, should change. We will see how. Now let's make a triangle. So let's make a triangle and observe what exactly is going, and how is it possible for us to keep the angle of attack alpha to be optimum. Now in the previous video we have discussed, we are interested to keep the angle of attack optimum, and we have discussed the optimum angle is 7 degrees. So what we are interested is to somehow maintain this 7 degrees. For that we have to maintain this angle. Can you see this angle? This angle is nothing but twist angle. Actually twist and pitch, but I don't want you to get confused. For now, just imagine this is the twist angle. That means somehow we have to maintain this angle such that the alpha angle of attack would be 7 degrees. I hope you're getting what I'm trying to say. So when we make the velocity triangle, it would become extremely clear to you what I'm talking about. Now imagine there are 20 elements. Now this blade is being cut into 20 elements, 20 partitions. Now let's observe. Let's make triangles. Let's make these triangles for all the 20 elements, but all the 20 elements are not possible. So let's make for 2 elements. Right? Now this is nothing but velocity of wind, right? So let's make it here. Right, so this is nothing but velocity of wind, or else let's cut and paste it, so that would be easier. So let's cut this and paste it here. Right, now imagine I'm sorry. Right, so now observe this figure very carefully. Now if you observe this figure carefully, you would observe that the velocity of wind right here is constant for all the elements. That means the velocity of wind here is equal to the velocity of wind here. That means all the elements are experiencing the same wind velocity. We are speaking about wind velocity, we are not speaking about relative velocity. The velocity of wind is equal, right? So this guy right here is constant for all the elements. The only thing changing, now even omega for all the elements, that means this element, this element, this element, for each and every element omega is constant. The only thing which is changing is the radius, that means the distance from the center of rotation. So if the radius is changing, naturally this vector, that means this vector is changing. I'll show you properly. This vector, which is the linear velocity of the element, is changing, but for all the element, the linear velocity is different now, but the velocity of wind is constant for all the elements. So now if we try to make this triangle for each and every element, you would observe that this vector, which is wind velocity, will remain constant for all the elements. The only thing which is going to change is this vector right here. This vector, which is the linear velocity of the element, would be different for different elements. It depends on the location from the center of axis. That means R is going to change for all the elements. So what will happen if R changes? Now let this be the triangle which is representing, or else I have one more idea. Let this be the triangle which is representing the element which is located nearest. Say for example this element right here. Say for example this triangle is representing the element which is nearest to the axis of rotation. Now please observe this very carefully. Now just see how the twist angle changes as the radius r of r changes, like the distance from the center of the rotation, that means the distance from this axis increases, how the twist changes and why it changes. Now I have shown three different blade elements. Say this is the first blade element. Now this blade element is which is closest to this axis of rotation, and then we have a second element which is in the middle, say somewhere over here, and we have the final element which is this element which is at the tip. So let's analyze the elements. So we have made three triangles. So this is for this element which is the nearest. If you carefully observe, now this phi is very big because radius is very small, isn't it? So this vector r omega, the linear velocity of the element, is small. That is the reason this phi has to be big, isn't it? So if this phi is big and this angle alpha, we want it to be 7 degrees. That means this angle beta, this angle right over here, this angle right over here is big. This angle is big. Why it is big? Because phi is big and we want alpha to be 7 degrees no matter what, because that is the best alpha at which we can get the best lift to drag coefficient, lift to drag ratio. So when the radius is small, you can see the twist is big. Say this should be around 45 degrees, say for example 50 degrees maybe, or 40 degrees, somewhere around. Now let's go to the middle element, this element right over here, and let's observe the amount of twist that we need to give. Now just observe carefully as the radius increases, right, it is this. As the radius increases, this is the middle element right over here, this element. So as the radius increases, now because this vector has increased, this phi has decreased, isn't it? It has to decrease because phi is basically tan inverse of 1 upon tip speed ratio. So anyways, so As the R increases, phi decreases. It has to decrease because the velocity of the wind is constant. So if the velocity of the wind is constant, naturally, if the linear velocity R, if even omega is constant for all the elements, so as the R increases, phi, which is angle of inclination, has to decrease. So what happens is this guy alpha, which is angle of attack, we want it to be constant, so again it's 7 degrees. But now you can clearly see this angle, which is beta, our twist angle, has decreased. I hope you are getting it. Now let's analyze the final element, which is this element, the final element right here, the last element. Now this element is having the tip speed ratio equals to 8 right over here. That means this element is experiencing the tip speed ratio of 8, but it doesn't mean that all the elements are experiencing the tip speed ratio of 8. That's the reason the angle of inclination phi changes, and hence we have to change the twist. I hope you're understanding this concept. Now let's observe this final element, and let's see what's going on there. So this is the final element. Now again, the velocity of wind is same for all the elements. The only thing that is changing is R. Now in this final element, R is maximum. R is 5 meters, for example. 5 meters is the length of the wind turbine, for example. So when R is maximum, naturally this vector right over here, linear velocity of the blade element, is maximum. That means the angle of inclination phi, this angle right over here, has to decrease even more. So this angle of inclination has decreased even more, and we want this guy alpha, that is our angle of attack, to be constant at 7 degrees. So naturally this angle has decreased even more compared to the other elements. So this angle beta has decreased even more, right? So we will again review the three elements. This element which was closest, had the twist angle biggest. It has to be biggest, isn't it? As you can see from the triangle, because our main intention is to have alpha, which is angle of attack, 7 degrees, because it has the best lift to drag coefficient. Now as we go to the middle element, we can see the twist angle has decreased because radius has increased, and we want alpha to be constant, so naturally our beta should compensate for it. So beta is lesser as compared to this element, which was the closest. This was the closest element, and this is a little far away from the center of rotation, so this has the angle beta has decreased even more, twist has decreased. And when we go to the final element, the element which is located farthest from the axis of rotation, phi, the angle of inclination, has decreased. So naturally if the angle of inclination has decreased, our beta has decreased, which is the angle of twist. So this is the way the twist of the blade, a twist of the wind turbine blade, is designed. Now you would ask a question. Now there could be a question that what is the base? What is the base on which the twist is designed? Now the answer is, now when we select a wind turbine, we select a location and we select the tip speed ratio at which we want the wind turbine to be operated. Now say for example, we decide that we want to design a wind turbine which should have a tip speed ratio of 8 right over here. Right over here. That means we know that the tip of the element, that means the final element of the blade, this element right over here, this element has to have the tip speed ratio of 8. Now if this guy has the tip speed ratio of 8, we can design twist for this element, and as we saw the triangle right now, we can imagine if this guy is tip speed ratio of 8, then we can easily calculate the tip speed ratios of each and every element along the blade, right? It's very easy to understand, but the concept is we select the tip speed ratio at which we want to design the wind turbine. Say if we want to design a wind turbine for a tip speed ratio of 8, then we can easily calculate the tip speed ratio of all the elements. It's very easy, isn't it? Just now we saw how to calculate. We only have to know the tip speed ratio of the final element, this element right over here. So this is how we calculate the twist. This is how we make the twist of the wind turbine. Now the question is, how do we know that the tip speed ratio is 8? For example, we make a wind turbine. How do we know that it will be operated at the tip speed ratio of 8? Because wind is random, everything is random. How is it possible that we will maintain this tip speed ratio? Now for this, what we do is we have a generator which is variable. In simple language, we can say we can vary the torque. So for now, just for understanding, I can say you that we'll discuss it later, how we change the torque of the generator, and the difference between the mechanical and electrical output, how it is maintained for this blade to achieve the tip speed ratio which we desire. For that, what we do, okay, we will come to it later, but for now I want you to understand that we decide a tip speed ratio, and by that tip speed ratio we can easily design the twist of each and every element of the wind turbine. So in the next video, what we will do is we will study the pitching. In these videos we are more into angles and stuff. In the later videos we will go into forces, and so the next video would be on pitching. So it would become very interesting how at different tip speed ratios it is possible to maintain the best possible coefficient of power by pitching it, right? So see you in the next video. Alright, see you then. Bye bye.